Okay, so in this video, we are considering our second example of a test of a hypothesis. The difference between this and the other video is that in the previous video, we considered a test of hypothesis for a deviation. Here we will consider a test of hypothesis for the mean. The problem is still the same. We had a bottle filler, and we wanted to test if it was still calibrated. But now, in C, we are testing for the mean, not the standard deviation. So as always, we formulate two hypotheses, and we give H naught the benefit of the doubt, so we will be under the assumption of H naught being true. And well, here's the question. We want to test the claim that the mean is different than 541 at the 5% level of significance. Well, the specifications mention that the mean was 541. H naught, if you remember, is the status quo hypothesis, the hypothesis of no change. So we give the specifications the benefit of the doubt. We assume that the bottle filler is still calibrated, and so that the mean is 541. And now, here we would have, in H1, the alternate hypothesis, two valid hypotheses, right? We obtain from our sample a mean of 540. So you have here two options. You could claim in H1 that mu is less than 541, but here, since we say we want to test the claim that the mean is different, if we had said specifically that the mean is less than 541, then we would go with, in H1, mu is less than 541, and have a left tail test. But since here we specifically ask to test the claim that the mean is different than 541, we will simply say in H1, mu is different than 541, and so we have a two-tailed test. Now, if I only said in C, to formulate a valid hypothesis about the mean, you could have picked this one, or since you obtain a sample mean of 540, you could have also said in H1 that I'll go with mu is less than 541. Both would be valid hypotheses, but since here our hands are tied, we are specifically asking to test the claim that the mean is different, hence not equal to 541. And we are testing at the 5% level of significance. So under the assumption of H naught, we are going to reject the more extreme 5% of values. Well, what do we have here? Right? Remember that we had a sample of 20 bottles, and we had obtained a sample mean of 540 milliliters. That's all we need to write down. We don't need to bother with, well, actually, that's not true. We need our sample deviation, right? We obtain a sample mean of 540 and a sample standard deviation of 2.6 mLs. Okay, well, we have a test for the mean, so we have to look at our test statistic. So we go with, since we are under the assumption of H naught, which is simply that mu is 541, we cannot use the claim that sigma is 2, right? Because this is a specification of the bottle filler. We don't know if this is true or not, and actually, in our previous problem, we had serious doubts as to whether sigma was 2 or not. So here we go with the safer approach by saying, well, we did obtain a sample of 20 bottles, and we found a sample mean of 540 and a sample deviation of 2.6, so we go with S being 2.6. Therefore, we will have a test statistic giving us the t distribution, being the sample mean minus the true mean over S over root of n, and this will be approximately a t random variable where the degrees of freedom, if you recall, are n minus 1. The sample size minus 1. So we have our test statistic. Let's look at our observed value of this test statistic. Again, Since we have a t distribution, we'll use the letter t. Subscript OBS for observed. And again, this is the observed value of our statistic under the assumption of h0. We give h0 the benefit of the doubt. So you say, okay, if h0 is true, here's our observed test statistic. X bar is 540, minus mu under h0 is 541, divided by s, which we found to be 2.6, over the root of n root of 20. Oh, and here I forgot to mention, obviously since n is 20, n minus 1 is 19. So we have 19 degrees of freedom. And if you use your calculator, let's compute this. So 540 minus 541 is negative 1, and we divide this by 2.6 divided by the root of 20, which will give you an observed test statistic for t of roughly negative 1.72. So we have our observed test statistic. At this point, again, we have two different approaches that are equivalent. We can use the p-value approach or the rejection region approach. Because of our tables, it is always more convenient to go with the rejection region approach. Well, which distribution are we going to draw? Since we have a t random variable, we will draw the t distribution, which we know resembles the standard normal distribution. It is symmetric about the mean, and the mean being 0. The only difference between the t and the z distribution is the z has slightly, has slightly heavier tails. And here, well, what is our rejection region? Well, let's see. We have a two-tailed test here. Mu is not equal to 541 is h1, and so we have to reject both the left tail and the right tail. If we said mu is bigger than 541, we would reject the right tail. If we said mu is less than 541, we would reject the left tail. But because h1 is mu is not 541, well, not 541 means either smaller or greater, so we reject both the left tail and the right tail of our distribution. And we have to reject in total, and this is really key, in total 5% of the more extreme values. By symmetry, that means that we reject 2.5% at both ends. So the area here is 0.025, and the area here is also 0.025. So both of these together will contain the more extreme 5% of t-scores. Well, now, recall that we had 19 degrees of freedom. We simply have to use our table for the t distribution to figure out what is the value of t in both of these cases. Our table gives you the area to the t-score, to the right. So we'll use the fact that to the right of our t-score, the area is 0.025 with 19 degrees of freedom. So let's see. Degrees of freedom and alpha, the area to the right, we had an area of 2.5% with 19 degrees of freedom. So you see that if you have an area to the right, let me just move up, of 2.5% with 19 degrees of freedom, the corresponding t-score has to be roughly 2.093. And so now we have our value of t for the rejection region. This is 2.093. And by symmetry, about t equals 0, this will be negative 2.093. And we now have our rejection region. R will be from negative infinity to negative 2.093. union 2.093 up to positive infinity. And now you say, okay, well, R contains the more extreme 5% of values, so is our observed t-score in or out of the rejection region? Well, our observed t-score was approximately negative 1.72, so it's approximately here, and this is not in the rejection region. And so what will you think of it? If we find an observed t-score value that is inside the rejection region, this would mean that under H0, we would have observed an event that is less than 5% likely to occur. Well, because our observed t-score is not in the rejection region, this is more than 5% likely to occur, so we give H0 the benefit of the doubt, and we do not reject it, we accept it. If, on the other hand, our observed t-score would have been an element of the rejection region, then the probability under H0 of observing such a t-score would be less than 5%. This would be too unlikely, and we would have rejected H0. But this is not the case here. And this concludes part A, right? We have to test the claim that the mean is different than 541 at the 5% level of significance. And our conclusion is that we give H0 the benefit of the doubt. We accept that the mean really is 541 milliliters. Now in D, we want to test the claim that now the mean is less than 541 at the same level of significance. So everything stays the same except that we will have mu is less than 541, therefore a left tail test. We still have the same t statistic, the same test statistic, and the same observed t value. The only difference will be our H1 and our rejection region. So this is D, and as you'll see, it'll be very quick. So again, we are under the assumption of H0. So we give H0 the benefit of the doubt. Therefore, the mean specified is still valid. We were specifically saying to test the claim that the mean was less than 541. So we have now a left tail test. We had a significance level of 5%. So because we had a t distribution, we draw again our t distribution. Because we have a left tail test, we reject the left tail of our distribution, and we reject, of course, the lower 5% of values because we have a significance level of 5%. And we have to find the t value here. Well, the table for the t distribution gives the t-score for an error to the right, but by symmetry, if you reflect this about 0, you'll get the error to the right is 5%, and you'll want the t-score, negate, and you'll get back the desired value. And we had, once again, a sample of 20, therefore 19 degrees of freedom. So we can go and read from our table of the t distribution. We'll take an area of 5%, and we have 19 degrees of freedom. So let's see. With an area of 5% to the right and 19 degrees of freedom, we find a t-score of 1.729. So you see that if the area here is 5% and we have 19 degrees of freedom, the t-score is 1.729. So we go back to our picture. This would be 1.729. Reflected, you get negative 1.729. And now we have our rejection region. Because we have a left tail test, we reject the lower 5% of values. So R will be going from negative infinity to negative 1.729. Well, is our observed t-value in or out of our rejection region? We had observed a value of t that was approximately negative 1.72, and it was actually negative 1.720. So it's really close, right, to being inside the rejection region, but we barely missed the cut. So it's not in the rejection region. So we end up accepting H naught once again. But it was a really close call. And you can see if we had observed a t-score that was inside the rejection region, the probability of such a t-score would be less than 5%. That would be too unlikely, and so we would reject H naught. But now, since our t-score is not in the rejection region, it is slightly more likely than 5%, and so we give H naught the benefit of the doubt and we accept it. Let's look at one last problem. Again, we have the same situation. We have this used bottle filler, and on E we're asking, what if a sample mean of now no longer 540 was obtained, but 539 was obtained? We want to formulate a proper hypothesis about the mean and test our claim at the 1% level of significance. Let's do this. Again, we will assume H naught. So we give H naught the benefit of the doubt that the mean is still calibrated at 541 milliliters. And H1, well, let's see. Now we are assuming here that we have obtained a sample mean of 539.4 milliliters. And so what do we believe is true about the mean? Well, here we would have two valid claims for H1. You can either go with, I believe that the mean, since we have obtained 539.4, is less than 541, or you could also be more conservative and say that the mean you believe is different than 541. With a sample mean of 539.4, it would be kind of hard to justify in H1 claiming that the mean is bigger than 541 when we have obtained an even smaller value. So here a left tail would be justified, and also a two-tailed test. We will go here with a left tail test. With the evidence we have gathered, it looks like the mean may be smaller than 541. So we have a left tail test. And now we have a different level of significance, which is 1%, 0.01. Let's compute our observed t-score. And here I won't write again test statistic, observed value. It's the same as before. So let's compute our observed t-score. This was again sample mean minus the true mean under the assumption of H naught over S root of n. The mean was, in this case, we assume was 439.4 minus under H naught 541 over 2.6 over the root of 20. If you compute this, you'll find an approximate value for your observed t-score of negative 2.752. All we need now is our rejection region. So since we have a t random variable, we draw the t-distribution. Because we have a left tail test, we will reject the smaller 1% of values. And once again, we had 19 degrees of freedom. So we have to extrapolate the given t-score here to build our rejection region. So we fall back to our table of the t-distribution. We'll find the positive t-value and then reflect it at the negative t-value. The area was 1% with 19 degrees of freedom. And so we have a t-score of 2.539. But 2.539 would be our t-score for the area to the right being 1%. If you reflect 2.539, you'll get negative 2.539. And now you can build your rejection region. R will be from negative infinity to negative 2.539. So this interval contains the smaller 1% of values. If you look at your observed t-score, it actually does belong to the rejection region. And once again, you ask, well, what does that mean? Well, if you ask, if I take a random sample, I obtain a random value of t, so random observed t-score, under the assumption of h0, the probability of observing a t-score inside of this interval is actually less than 1%. Since our observed t-score is in the rejection region, under h0, under assuming h0 was true, we have just observed a value that was less than 1% likely of being observed. This is too unlikely. We don't have faith in h0, therefore we reject it in favor of accepting h1. So there is enough evidence against h0 to accept h1. So from the data gathered, it looks like the true mean from a sample mean of 539.4 and a sample deviation of 2.6, it looks like the true mean is more likely less than 541, so the bottle filler is no longer calibrated.